Welcome to the presentation of the paper Encryption Schemes using Random Oracles, from Classical to Post-Quantum Security. My name is Patrick Struck, and this is joint work with Juliane Krämer, and we're both from TU Darmstadt. Let's start with the background and some motivation for this work. So we're looking into public key encryption schemes where we have two communicating parties, Alice and Bob. And Alice, who knows Bob's public key, wants to send some message M to Bob. Then what Alice will do is she runs the encryption algorithm on Bob's public key and this message she wants to send to derive some ciphertext C. Then when Bob receives the ciphertext C, he can use the corresponding secret key, run the decryption algorithm on these two inputs to get back the message. And then in between we have the adversary who will be able to observe the communication, so the adversary will be able to observe the ciphertext C and then try to derive some information about the underlying message. Regarding security for public key encryption schemes, there are two main security notions. The first one, which is also considered as passive security, is indistinguishability under chosen plaintext attack, or INDCPA for short. So this is modeled as a game which consists of three phases: a learning phase, a challenge phase, and then another learning phase. In the first learning phase, the adversary gets a public key of the encryption scheme. Then during this phase, the adversary can use this public key in order to encrypt arbitrary messages of its choice. At the end of the learning phase, the adversary is supposed to output two messages, M0 and M1. These are then sent in the challenge phase to some challenger. Then the challenger will sample a bit B at random and then either encrypt the message M0 or the message M1 of the adversary to compute the challenge ciphertext CB. Then this challenge ciphertext CB is sent over to the adversary, who then in the second learning phase can again use the public key in order to encrypt arbitrary messages of its choice. At the end of this learning phase, the adversary is supposed to output some bit B prime, and the adversary wins the game if this bit B prime equals the bit B chosen by the challenger. And a scheme is considered INDCPA secure if the chance of the adversary in winning this game is roughly 1/2. Now the second notion, which is active security, this is called indistinguishability under chosen ciphertext attack, or INDCCA security. Again, we have the three phases, and the overall picture looks very similar. The main difference now is that in this learning phases, the adversary also gets access to a decryption oracle. So the adversary can ask for the decryption of arbitrary ciphertext. The only restriction now is that in the second learning phase, the adversary is not allowed to ask for decryption on this challenge ciphertext CB, as this would trivially allow to win the game. And now for both of these security notions, when the schemes use random oracles, these learning phases are enhanced by granting the adversary also access to a random oracle in these phases. Now in general, for public key encryption schemes, we always aim for security against chosen ciphertext attacks. But the main problem is that it's hard to design schemes that achieve INDCCA security from scratch. Luckily, there's a solution proposed by Fujisaki and Okamoto in 1999, which is called the Fujisaki-Okamoto transformation. What this transformation does is it takes an INDCPA secure encryption scheme, and then via first transformation T, it transforms this scheme into a one-way CPA secure encryption scheme. And then via a second transformation, it transforms this one-way CPA secure encryption scheme into an INDCCA secure encryption scheme. So this means that for all the schemes we want to design, we need to focus on proving them INDCPA secure, and then we can achieve INDCCA security using this Fujisaki-Okamoto transformation. The Fujisaki-Okamoto transformation has also been analyzed in the post-quantum setting, for instance by Tagi and Unruh in 2016 and by Hofeins, Höfelmans and Kills in 2017. They essentially show that the transformation is also valid against quantum adversaries, So if we have a scheme which achieves INDCPA security against quantum adversary, or it is post-quantum INDCPA secure, then the transformation gives us a post-quantum INDCCA secure encryption scheme. So this means that the goal now is to achieve post-quantum INDCPA security and then use the generic transformation in order to get the desired post-quantum INDCCA security. And well, for most of the public key encryption schemes that are proposed as quantum resistant schemes, this is easy, and this includes basically all the schemes that are proven secure in the standard model, because there the proof easily translates also against quantum adversaries. But for the schemes that are based on random oracles, the situation is more difficult, and this also defines the focus of this work. And the reason for this is due to the quantum random oracle model. But let's go a step back and first review the random oracle model. So this was proposed by Bellard and Roggeway in 1993. So we have the adversary, and the adversary gets access to some random oracle H. What the adversary can do is can send some input X to the random oracle and then get back the output H of X of the random oracle. And this is the model we use to prove certain schemes secure. And then in real world, what we do is we instantiate the random oracle using a hash function. And this then gave rise to the quantum random oracle model proposed by Bonnet et al. In 2011. And the reason there is they observed that since the hash function is public, if we have a quantum adversary, what the quantum adversary can do is it can implement this hash function on its quantum computer and therefore evaluate it on a superposition of inputs. And this now gave rise to this quantum random oracle model where we have the adversary, and instead of just asking the quantum random oracle on classical inputs, the adversary can ask the oracle on a superposition of inputs. And in return, the oracle will send back the corresponding outputs in a superposition. And now in general, when we're considering classical adversaries, we conduct the proofs in the random oracle model. But whenever we want to achieve security against quantum adversaries, the proof should be conducted in the quantum random oracle model. Now, what does this mean for our security notion? So if we look at this post-quantum INDCPA security in the quantum random oracle model, we have this picture we've seen earlier now with the quantum adversary. And now in the learning phases, the adversary also gets access to a quantum random oracle. And this is in contrast to the classical setting where there would only be a classical random oracle for the adversary here. Now with this we come to our main contribution. So we want to lift security from the classical to the post-quantum setting. More precisely, we want to lift INDCPA security proofs, which are conducted in the random oracle model, to post-quantum INDCPA security conducted in the quantum random oracle model. Now when we look at the classical proofs in the random oracle model, they all have a very similar structure. So there's some game G0, which is the INDCPA security game instantiated with the concrete encryption scheme. Then there's another game GK, which is an ideal game, where ideal game in this sense means that the challenge ciphertext CB, which encrypts either of the two messages M0 or M1 of the adversary, is actually independent of the secret bit. So in this ideal game, the adversary can only guess whether the bit was 0 or 1. Now this means that to prove a scheme INDCPA secure, what one can prove is that the adversary cannot distinguish this real game, G0, from this ideal game, GK. To make the proof easier and feasible, there are several more games in between, G1 to GK-1, such that the difference between each pair of consecutive games is small. Now, to bound the overall advantage of an adversary in distinguishing this game G0 from GK, one can bound each of these game hops individually. So we can bound the advantage in distinguishing G0 from G1, G1 from G2, and so on. Now this proof approach carries over in the post-quantum setting. So The main reason is that the ciphertext remains classical even against the quantum adversary. So this means that the game GK is also ideal against the quantum adversary. But now the main challenge is that each of these game hops has to be proven in the quantum random oracle model, while the classical proof was done in the random oracle model. Now, we're not able to arbitrarily lift security proofs from INDCPA to post-quantum INDCPA. Instead, what we do is we define a certain class of encryption scheme for which we then can show how to lift security. And this class of encryption scheme is what we call Oracle simple encryption schemes. And here you can see how these Oracle simple encryption schemes look like. And it's a restriction on the way the encryption algorithm works with the random oracle. Now, here we have the encryption algorithm, and for an Oracle simple encryption scheme, the encryption algorithm does the following. So it first will sample a value R at random. It then applies some deterministic function f to R to get some value x, and then invoke the random oracle on this value x to get the output y. And then the actual ciphertext is computed using a subroutine EncSub, which then takes the public key, the message, this randomly sampled value R, and the output y of the random oracle as input, and then output the ciphertext. The main thing here is that the subroutine EncSub is independent of the random oracle, so it has no access to it. And this way, as you can see, everything that's related to the random oracle happens in the first part of the encryption, and it also happens in a bit of a restricted way. Now, some example schemes which are Oracle simple are the code-based encryption scheme Rollo2, which was a round 2 candidate in the NIST standardization process. Then the lattice-based encryption scheme Lara by El-Banzakani from 2019. And also the code-based encryption scheme BigQuake, which was a round 1 candidate in the NIST standardization process. Now, in general, this Oracle simple might seem a bit restrictive, but actually we're not aware of a random oracle-based public key encryption scheme which is not covered by this definition. Now, what these Oracle simple encryption schemes allow us is to divide the game hops in the proofs into 2 different types. So one, we have the game hops which are then independent of the random oracle. This is what we call type 1 game hops. And then the game hops which are actually dependent on the random oracle. This is what we call type 2 game hops. Now let's look into type 1 game hops. So here we have a game GI, which uses an Oracle simple encryption scheme. And a type 1 game hop would be now a game hop to the following game GI plus 1, where the 2 games, GI and GI plus 1, agree on the first part, so the random oracle related part. And then they only differ in this subroutine EncSub that the 2 games use. So more precisely, in game GI, the subroutine EncSub will be used, and in game GI plus 1, a slightly different variant EncSub prime will be used. Now, from this, it's actually quite easy to see that the difference is now independent of the random oracle, because the subroutines are independent of the random oracle. And this gives us the following, namely the classical reduction basically just goes through in the quantum random oracle model. Because for this proof, the reduction only needs to be able to simulate a quantum random oracle for the adversary. And this is doable by using Q-wise independent functions, for which Stantry has shown in 2012 that an adversary cannot distinguish a real quantum random oracle from one which is simulated using a Q-wise independent function. Now, type 2 game hops look as follows. So we have a game GI, which uses this Oracle simple encryption scheme. And then the type 2 game hop would be to another game GI plus 1, which differ in how the value y is sampled. Namely, in game GI plus 1, the value y is sampled at random, independent of the random oracle. Now, in the classical setting, this game hop is bound by the probability that the adversary makes a random oracle query on the value x. Because as long as the adversary never invokes the random oracle on x, these two games are perfectly indistinguishable for the adversary. Now this argument does not work in the post-quantum setting because of these queries in superposition. So if the adversary makes an equal superposition query, it somehow has queried the value x, although we don't expect that this query would enable the adversary to actually have enough information about the random oracle on x to detect the difference between these two games. Now instead, what we do in the post-quantum setting here is to use the one-way-to-hiding lemma proposed by Unruh in 2015. Now for this, we can view this type 2 game hop slightly different, and essentially in the following way: that in game GI, the adversary has access to a quantum random oracle H. And in game GI+1, the adversary has access to a slightly different quantum random oracle H prime. In the way that these two quantum random oracles, H and H prime, agree on all their inputs except for this particular input X. So if the adversary can distinguish these two quantum random oracles, then it can distinguish these two games. Now to bound this, what we can do is consider an adversary has access to H, and that phi1 to phi-q denote the queries that the adversary makes to this quantum random oracle H. Now we can construct an adversary B who will simulate the oracle H for the adversary. And then what B will do is it picks a value I at random from 1 to q. And then for the ith query of the adversary, when the adversary queries phi I to the random oracle, the adversary B will simply take this query, measure it, and output the result. Now this is exactly what the one-way-to-hiding lemma is bounding. So the one-way-to-hiding lemma bounds the chance that the adversary distinguishes the two games here on the left side, so the type 2 game hop, by the chance that the adversary B on the right side, that simply measures a randomly chosen query by the adversary, that this one actually outputs the value x on which the two oracles disagree. So this gives the intuition that to actually distinguish between these two oracles, there has to be one query which then will be measured to the value x. And now with this, we're coming back to the setting that we can use from the classical proof, namely that we can bound the probability that B outputs the value x where the oracles disagree by using the classical proof. And now if the proof uses a quantum hard search problem to bound the probability of finding this value x, then this proof goes through in the post-quantum setting. To prove Oracle simple encryption schemes to be pqINDCPA secure, we proceed as follows. So we take the classical proof with the games G0 to GK, and then we go over the different game hops one by one, and then we classify these game hops as either type 1 or type 2 game hop, and then analyze whether some quantum hard problem is reduced to bound each of these game hops. And due to the structure of Oracle simple encryption schemes, there will be one type 2 game hop because the encryption scheme invokes the random oracle only once, while all the other game hops, they will be type 2 game hops. So to wrap up, in this work we studied how classical INDCPA security can be lifted to post-quantum INDCPA security for public key encryption schemes that are based on random oracles. Now, since we were unable to generally lift security for public key encryption schemes, we came up with the definition of Oracle simple encryption schemes. And for these Oracle simple encryption schemes, we showed how the different game hops of the classical proof can be lifted to the post-quantum setting. And as the final contribution, we used these results to show that the code-based encryption scheme Rollo2 and the lattice-based encryption scheme Lara are both post-quantum INDCPA secure. This concludes my presentation. Thank you very much.